Guys, in this video, we're going to talk about our next part of the procedure, maybe if this is the order that you're going in, and it's going to be another gravimetry, but it's going to be called chemical gravimetry. And the reason we call it chemical gravimetry is because we are going to get a product, we are going to weigh that product, and we are going to use that mass in our calculation. So that by definition fits gravimetry, but in order to get to that point, we're going to really have to go through a series of different chemical equations. So we're going to have to start off using one thing to make another, which we will be using that to make another, which will be used to make another, and then finally we get to the point of that precipitate in the very end. But that's why we're calling this chemical gravimetry. It's not just a simple, let's dissolve one thing away and then have that product, which is copper, untouched. We're really going to have to fully dissolve everything in this case and then bring it back to see if these are going to produce a little more reliable numbers for us with this particular method. All right, so when you pull up the lab procedure, what you're going to see is another very abbreviated lab. And it looks like just a handful of steps here, and they don't really look complicated, quite honestly. If you take a look at step number 1, it says cut the 2 pennies in half, and then weigh and place the halves in separate 250 ml beakers. So again, make sure you're picking the right date of the penny, but we're going to completely cleave it in two parts. Number 2, in the hood, in all capital letters, add 20 mils of 6 normal HNO3 and allow to dissolve. And when it fully dissolves, you add a little bit of water just to increase the volume of these solutions so you can do other things with them. All right. If you don't, then you're going to get maybe some problems later on down the road when you begin to add the other reagents. All right. So let's kind of talk about the reaction that's happening here. So we've got copper and we have zinc, and both of these are basically in the penny, right? And we are adding nitric acid to it this time. Now, this is going to be different than hydrochloric. Nitric acid loves metals. And due to the single replacement chart and the reactivity chart according to acids, metals typically respond very well to HNO3. So if I add nitric acid, the problem here is that it's going to dissolve both, not just one. Right? In the first part, hydrochloric targeted zinc only, and it left copper behind. It didn't care anything for it. But nitric acid will actually dissolve both of these up. So what we'll end up with is copper and nitrate coming together, and we'll end up with zinc and nitrate coming together, and then off pops hydrogen. Now, single replacement still going on. There's just 2 reactions happening at the same time. A single replacement between copper and nitric acid, and then a separate single replacement between the zinc and the nitric acid. Okay? So that's why I'm kind of drawing it the way that I am, just to save a little bit of space and maybe some confusion that might happen. All right, well, copper and nitrate are not balanced. Zinc and nitrate's probably not balanced. We want to go through and take a look at these guys. So copper is a positive 2 charge in this reaction, and nitrate, NO3, is a -1. So I'm probably going to have 2 of these to make this work. Zinc is going to be the same way. Zinc is a positive 2, and it's going to take 2 nitrates in order for that thing to be balanced. So that way it can be happy, and it doesn't want to break down unless we do something else to it. And then finally the H, well, it's diatomic and it can't be by itself, so that has to be an H2 before we go further. All right, so copper and zinc both are going to be fully dissolved. Fully dissolved. All right, and anytime we have a copper solution, it tends to be a very particular color, and these colors can go anywhere from green to blue. Greenish blue, maybe somewhere in the middle. But those tend to be the colors that we would associate with a copper solution here. All right. So expect that when it happens. Now, the reason that we're telling you to do this under the fume hood is because it is generating hydrogen gas, right? And we did really the same thing for part 1. We put hydrochloric acid in the beaker, and in those directions, it did tell you to keep it under the hood. Allow it to do its thing, but make sure it's under the hood. Same concept there. It's generating hydrogen gas. And here we're generating hydrogen gas, but nitric will also give off nasty, stinky fumes. And it can stain at the same time. So we don't want to be breathing in all of those extra fumes with this reaction that's taking place. It's also going to generate quite a bit of heat for you as well. All right, so after this reaction is over, it will completely dissolve all of the metals. We get copper nitrate and zinc nitrate in solution. We're then going to add some water. It's not going to change anything at all at this point. It's just going to increase our volume, and that's about it. All right, we've actually had people not to add water before, and the reaction still goes forward. They might just have a harder time seeing what they should be seeing. All right, so step number 3 says after you do this, we're going to add another reagent, and that reagent is a 6-normal ammonium hydroxide until you get a faint precipitate. All right. So we're going to take this copper product, CuNO3, and we're going to add to this a little bit of ammonium hydroxide. Now, when you do this, you need to keep in mind this is a base and it's very stinky. It's ammonia here, so it's going to smell like cat pee. So you'll probably want to do this under the fume hood as well, because if you don't, it's going to stink you out. So we've got this copper nitrate. We're going to react it with ammonium hydroxide. Notice now up at the top, I did not balance the equation. Okay, I didn't balance it. So if I go back up here to the top, there is a 2 for the NO3 group and a 2 for the NO3 group now. And now there's 2 hydrogens to the left, and now there's 2 hydrogens on the right-hand side of that arrow. All right, so that's the only thing I had to do. So in this case, what will happen is that the copper and the OH group will come in together, and they will form a relationship, CuOH. And then this NH4 and the NO3 group will also form a new relationship. Now, this is not a single replacement here. This is actually a double replacement. And a lot of people get confused because they can't really determine the difference between a single and a double replacement sometimes. Well, this is how you need to think about it. CuNO3, that is a compound, right? In the single replacement version, like up here, that copper's on his own. The copper single goes into a bar. There's an HNO3 couple that's there. Well, copper determines to be a little dirty, and he kicks hydrogen to the curb, and he takes over hydrogen's spot, and away we get a new compound. Well, in the double replacement, this is a couple that walks into a bar, and this is a couple that walks into the bar, and they swing. They're swingers. So the NH4 and the Cu switch spots, and those partners flip. So instead of CuNO3, it is now an NH4NO3, and that's what I've written over here to the right. And instead of an NH4OH, it is now a CuOH. Just like before, though, we want to balance these pieces before we go any further. Copper is a positive 2. Hydroxide is a negative 1. So because of that, I need 2 of those to make that thing happy. The ammonium, NH4, is a positive 1, and the NO3 is a negative 1. So these are okay. I don't need to do anything extra to those at all right? The problem here is that I need the equation to be balanced, and I can do that really quick. It looks like I've got 1 copper to the left and 1 copper to the right. I have 2 NO3 groups to the left. Well, I only have 1 of the NO3 groups here. So I can't split it up. I only can write big numbers out in front, big coefficients. So I'm going to put a 2 out in front, and now there's 2 NO3 groups. The NH4 group, I see there's just 1 of those. And here I see now there's 2 NH4 groups, and that's not going to work. So I'm going to have to put a big 2 here, so that way I can have the same number of ammoniums. And then finally, there are 2 OH groups that are to the left, and now there's 2 OH groups to the right. Okay? So this is what's going to happen in the next step. I've dissolved the copper and the zinc, though. I can't forget about that. And now I'm really playing off of my copper from this point on. That's really what we're focused on. That's where we're going to end up. So I'm only going to focus on the copper compound. So copper nitrate is going to react with ammonium hydroxide, and I get this copper hydroxide that begins to get formed. Now, if I go back to the directions, it's going to say add ammonium hydroxide until a faint precipitate happens. If I use the rules of solubility, my faint precipitate is coming from this copper hydroxide product. Now, you're probably thinking, well, what are the solubility rules? Maybe my Chemistry 151 didn't cover that for me. Well, I got news for you. I'm going to show you. So here it is, a solubility chart. And this is typically what you would find in any chemistry text. Now, at the very bottom, you're going to see insoluble compounds. Insoluble means it's going to precipitate out. And underneath that category, you see the word hydroxide. And they give you the OH right beside of that to let you know what hydroxides are. Well, guess what, folks? We've got a hydroxide here. Comes along with copper. And all hydroxides are insoluble. That means they're going to precipitate out. So that precipitate that you're going to see in that step, it's going to be the copper hydroxide. Over here to the right, it says soluble exceptions. Compounds containing alkali metals and the barium. So if I have an OH that maybe has NaOH, that's an alkali metal. KOH, that's an alkali metal. Or BaOH2, because it specifically lists Ba there, these things are going to stay dissolved. They will not precipitate out on me. All right? Now, keep in mind that zinc is still there. Zinc is lurking in the background, but we're only focused on copper. That's it. So do not forget that reactions can happen with zinc as well throughout this entire process. And this is why it's going to take more and more steps so we can start getting rid of some of that zinc that's coming along through the picture and along for the ride. So this is just the very first step in that process, and that's why. Okay. Next, it says add 25 mils of a 1 molar H2SO4. All right, so what would be happening here? Well, we get this precipitate, CuOH2, and now we're going to add H2SO4 to this. So this is a hydroxide. It's going to react with an acid, and it looks like a double replacement is going to happen again, right? This falls under a double replacement as well. Both of these do. So the Cu and the H will switch places, and we get this Cu and SO4 that come together, and the H and the OH switch, or the H and the Cu switch places there, so the H and the OH come together, and that really makes water. So I'm just going to rewrite it, right? HOH is water. Copper is a positive 2. Sulfate is a negative 2. So I don't need to do anything here. That is balanced. I'm okay with that. I've checked it off. That's good to go. The HOH, the H is a positive 1. The OH is a minus 1. So we know from experience water's neutral. There's no full charge on that compound, and that's why. Hydrogen's a positive 1, and OH is a negative 1. So they cancel each other out of there. So now I can go through and maybe balance this chemical equation, right? So I've got 1 copper to the left, 1 copper to the right. I've got 2 OH groups over here to the side. And you're probably thinking, well, wait a minute. This is kind of weird because there's no OHs over here. Yeah, there is. I'm just going to rewrite this up here at the very top. It's going to make it a little bit easier maybe. So 2 OH groups. Well, I have 1 OH group here. So I'm going to put a big 2 out in front. There's 2 hydrogens to the left, Well, now I got 2 times 2. That's going to be 4, but don't be confused because look up here at the top. We rewrote it, right? We've already taken into account one of the hydrogens with the OH. So this is 2 hydrogens on the right, and it's 2 OHs on the right. 2 OHs on the left, 2 hydrogens on the left. So that's good to go. And then we have a sulfate on the left and 1 sulfate on the right. So this thing is balanced, and this is that part of the reaction. So copper hydroxide, copper 2 hydroxide, reacting with sulfuric acid to give me copper 2 sulfate and 2 waters, if you want to keep track of moles and molarities and ratios all the way through this process. All right, next step, we're not done. It says now we're going to add 25 milliliters of a 5% NaHSO3. Now, we put in parentheses behind here sodium bisulfite, just so that you don't make the mistake of picking bisulfate, HSO4. We wanted you to pay attention here. This is a sulfite, not a sulfate. And if you grab the wrong stuff, then this probably is not going to work out for you very well. So now we want to talk about that reaction too. Okay, so what's going to happen here? Well, now what will happen is that we have this copper sulfate, and we're going to throw into the mix now this sodium bisulfite. It's similar, but it's not the same as sulfate. Now, keep in mind there's also water. Okay, there's water that's being produced. Right here is evident of it. The acids are all in water. The ammonium hydroxide's in water. Everything's in water. Water's always lingering around. But we're going to add sodium bisulfite. So the same type of thing is going to happen here. Reactions are going to take place. Things are going to kind of go through the ringer. But this reaction is a little different than the other two above. Not really a full-blown double replacement is going to happen. Instead, copper finally is kicked to the curb. Bye-bye. You had your fun, and now all fun comes to an end. So copper goes off on his own. All right, well, what do we make it now? Well, this H, or the SO4, we'll start there. This SO4 group can start to pull hydrogen from the water. And we can generate H2SO4, sulfuric acid. And the NaHSO3 can take some of that remaining oxygen because it pulled 2 hydrogens from that water molecule, right? And we've got an oxygen that's left over. And it can kind of stay together, but add somebody else into the mix. They get kind of kinky. So now we have NaHSO4 instead of NaHSO3. Now, this copper is going to stay in solution. And the reason is because it is acidified. It's not going to precipitate out just yet. It's getting close to that point, but not yet. And this is why. Okay? We're still in an acidified solution. We've already seen that copper likes to have some acid to dissolve in, and we have generated it right there. So this is not just water to allow copper to precipitate out, but copper's still around, still swimming in solution. And then we add in our next reagent. So we've got this copper that is present, and our next reagent is going to be ammonium, NH4, SCN. So this copper, because it's not precipitated out, is dissolved, which also means that there is a charge. Now, what we done before was a redox, and I'm not going to go through a redox background. No need for that here. But that previous reaction changed the charge on copper. And what we ended up with is a +1, not a +2. The whole time, all the way through, was +2, +2, +2, and then we finally get to a +1. We play around with the charges, and that's called a redox reaction. I'm not going to go through those steps, but that's what that is. So we've got this copper in solution. We throw in ammonium thiocyanate. This stuff will also stink. It will not smell very good at all. Well, from above, I'm going to go ahead and tell you that this is going to require 2 of them. So 2 of the coppers will react. Sorry, I'm thinking redox. Let me take that back. 2 of the coppers will react in the redox part, not in here. And a single replacement will happen. So the copper comes in, takes ammonia's spot, and we're left with CuSCN, and the ammonia or ammonium goes away. Now that ammonium will eventually turn into ammonia, which is NH3. That is a different product, different reaction that goes on, and we're left with some H2 gas that might be generated, so bubbles could be formed here as well. But this is the product that's important, because this is my precipitate here. And this precipitate is all copper. At this point, there is no zinc that should be left behind. The zinc should have stayed dissolved in solution, and I should not have any interference with zinc precipitate in this part of the reaction. This precipitate should purely be a copper precipitate, and that is it. So this precipitate is copper thiocyanate, CuSCN. Now, it says, when I get my product, my precipitate here, warm it for 5 to 10 minutes on a hot plate, filter through a pre-weighed filter, Gooch crucible with the filter. This is not a Buckner funnel. These are going to be one of those tiny little Gooch crucibles that we're going to be using with the tiny little holes in the very bottom. If you don't know where those are, you need to let us know so we can show you. And rinse it with large amounts of DI. If you do not rinse it with large DI, large amount, you have acid that's left over, and you need to get rid of all of that. It's going to oxidize it, and your product's going to turn black. And if it does, then this whole process has been ruined. You will not be able to get a weight. That weight will not represent your copper precipitate. It will represent something different. Number 9 says oven dry and then weigh again. Number 10, determine the weight of the copper thiocyanate and then the weight of the copper. Once you get that, you can then determine the percentage of copper. Now, how do I determine the weight of copper thiocyanate? Well, that's just the filter difference. What was the filter before? What is the filter after? You subtract the two to get your precipitate weight, right? So that's okay. That should be like very basic wet chemistry kind of stuff. Well, once I get the weight of the precipitate, how do I get the weight of the copper? Well, this goes by percentage, all right? So what I would do is I would take copper thiocyanate, CuSCN, and do a formula weight of it. Get the formula weight of the entire compound. And then I'll take a look at copper, and I'll do the formula weight of just copper, and that is it. And we'll do a percent composition calculation. That's all that this is leading to. You've done this before in our program, especially if you've taken the 150 class, the standards and solutions. So I would take the formula weight of my copper, and I would divide it by the formula weight of the copper thiocyanate, and that will give me the percentage, multiply by 100, and that will give me the percentage of copper according to the thiocyanate. And whatever that percentage is, I'm not going to do it for you. I want you to do it on your own. But whatever that percentage is, you're going to take that percentage and you're going to multiply it by your precipitate weight. For example, if my precipitate weighed 0.8312 grams, and let's say I do this calculation up here, and I get 33%. That means that 33% of this weight represents just copper, and that's it. So I'll take 0.33 and I multiply it by the weight, and I will get the gram of just the copper that is part of that precipitate. Well, once I get the gram of that copper, I'm then going to do the same thing as I did in step number 1. I'm going to take the gram of the penny half that I used. I take those two amounts, divide them, multiply by a 100, and this will give me the percent of copper that was in that penny. And then I compare that number to 2.5%. Hopefully I'll get something close. The problem here is that people get confused. And what they get confused about is the percentage that's over here. That has nothing to do with the 2.5% that we're trying to end up with. All this calculation is here is to determine, listen, I've got this compound. This compound is a precipitate. It has other things other than copper with it. Thiocyanate is also present. So I need to figure out if this is the weight of my precipitate, how much of that is really contributed to copper. And that's why we have to do what we do here. This is a percent composition calculation. You need to figure out how much copper contributes to copper thiocyanate. And then when you find that percentage, you multiply by the precipitate weight that you received, and that will give you the gram of copper that's present in that precipitate. Once you get that number, then you can calculate the percentage that we're after. Copper divided by the gram of the penny, multiplied by 100, and that gives you percent of copper. All right? Okay, so let me kind of show you the spreadsheet for that section. I'm just going to scroll down. Here you're going to see multiple different ones. So chemical gravimetry, again, we need the date here. So 1991 maybe, and this one was 1994. And it looks like I did penny 1B. So this also came from the 1991 penny because we cut it in half, remember? And then here is 1994. All right, well, the mass of the half is 1.0818 gram. The mass of the clean Gooch crucible that had nothing in it in the beginning, 20.1749. The mass of the Gooch crucible plus the precipitate in the very end after I added all of these reagents, right? Everything gets added in the same test tubes beakers. I don't do anything. I don't get any kind of data. I only work to the very end product. That's 20.2286. The mass of the precipitate, that of course is the subtraction of those two. Mass of the precipitate and Gooch minus the mass of the Gooch. That gives me 0.0537. To get the mass of the copper, I'm not going to click on that cell because I'm not going to spoil it for you, but this is where you're going to have to kind of calculate the percentage of copper in copper thiocyanate. And then when you get that percentage, you'll be able to multiply that by 0.0537, and you will get 0.0281 or something maybe close. And that represents the mass of copper only, not copper thiocyanate. Finally, what I would do is I would take that number, mass of my copper, and I would divide it by the mass of the penny from the very get-go, 1.0818, and I would multiply by a 100 to get percent of copper. And hopefully I'll get something close to 2.5. So if I look here, I get 2.5 there, 2.95 there. Here I have 2.45. Here I have 2.55. And I'm going to average all those up, and I get 2.64 with the standard deviation that's listed. And the accepted value, again, is 2.5%. So it looks like chemical gravimetry based on percent error is going to be way better, right? In the previous example that we talked about for part 1, that was a 20% error for just zinc removal. Well, here, the chemical gravimetry part, based on my data, yours might look a little different, but based on the data that I have here on the spreadsheet, is going to be 6%. That cuts my error more than half. So by far, chemical gravimetry, based on my data, is going to be a better method than the zinc removal. Again, yours could be something different. This is just what mine says. All right? Okay, so that's it of the second part, and the second part is the chemical gravimetry. Now, notice here it says part 3. The reason it says part 3 is because there is a piece, part 2, that's the electrograv. And this we have skipped, and the reason is because our electrograv does not work. We have a broken paddle, and until we get $2,500 to replace that broken paddle, we're just not going to be able to use it. So if you're required to do that section, you'll see a proper folder that will want you to kind of review that piece and do that piece, and I'll show you the calculations and the spreadsheets for that. But if you do not see that section listed, then that means we don't want you to do it. So that's why this says part 3 in the lab write-up. Okay. Notice in the directions it says 4 trials here. Again, this could be different. We could change this on you depending on the year. But the way it's written right now, this is penny 1 split into 2 pieces and penny 2 split into 2 pieces. You average those up, do a standard deviation, and do a percent error. All right, so that's all there is with the chemical gravimetry. A couple of reagents, add them to a beaker, get a precipitate, filter it through, weigh it, and do a very good job with your transfers, and I think that you'll have some very good numbers. So that's it for this lecture module portion, and then in the next laboratory folder, you'll see the next method that we'll do concerning a penny.